Hello, good morning, good afternoon, good evening. You have reached Saturday Science Chats. Yes, I'm Dave D. Hilscher, and welcome again. You have reached our Saturday Science Chats, sponsored by the John Chappell Natural Philosophy Society and Dissident Science Channel. Let's keep moving here, Dave. Today we've got a great show, an absolutely great show. We're doing a series now, and people are preparing for this, and this is our first in the series this year. They'll be scattered amongst all of our other things, including speakers and all that. And this series, we have talked about what the title should be, and we've come to like this title from our directorate, and we're calling it The Evolving Perspectives on the History of Science, meaning what we get taught in school isn't the latest because things are constantly evolving. But of course, we never hear that in our universities or in popular science magazines. They sort of at times say that they're going to be talking about critical thinkers and what they're doing outside of mainstream, but nope, we are going to do it. So we're going to be talking about the history of quantum mechanics today. Eric Reiter, who's an expert in that area, you've seen him before. If you don't know him and his work, check him out. Check out our channels, both Dissident Science and the CMPS. Just search for Eric Reiter, CMPS, or Dissident Science, and you'll see his talk on quantum mechanics. See here, this is a picture I love. Eric's just I wouldn't call this tinkering because that's way beyond tinkering in that picture there. But Eric's a great mind. I always love him talking. He's really got a different perspective, and that's what you come here for, not to hear the same old, same old. So, and again, I want to congratulate all of you for watching. It's extremely important. As Aristotle says, it is the mark of an educated mind to be able to entertain a thought without accepting it. What does that mean? It means when somebody comes up with a different idea and they say that what you think is true is not true, you got to be open-minded to that. So it's very, very important that we always keep that way, because if you don't, you get stuck, and that means you'll be stuck in the flat earth society while everybody else is watching the earth as a sphere and you're left behind. So it's always good to look at new perspectives of things. So we really want to preach. I really appreciate you guys' patronage watching this, and make sure you please subscribe, hit the like as well. If you're watching this right now, just hit the like. Even if you're not if you're just passing by, think, hey, I want to support people thinking outside the mainstream who are real scientists, then please click that like button and subscribe. And so that you know when our next videos come up, because if you subscribe, you'll get alerted to that. So, and I do want to thank again, we're coming up to 1,000 subscribers on the John Chappell Natural Philosophy Society, and I passed 4,000 subscribers. Thank you so much on the Dissident Science channel. So I really appreciate all that. Of course, the CMPS, or the Chappell Natural Philosophy Society, the mission is to be an organization that above all promotes critical thinking without malice, to be an organization that supports, publishes, and promotes serious scientific work outside the mainstream science, to provide a forum for open debate in modern topics in physics, cosmology, philosophy, and mathematics, to provide a forum for presenting serious papers and theories without fear of censorship, and to be run entirely by its membership. Now, it would be really nice that universities did this. Universities should be doing this. It's absolutely ridiculous. You should be able to write your PhD thesis and arguments of how the Big Bang is wrong, that an eternal universe is and all evolving internal universe is what should be correct. But of course, we're not allowed to do that, and it's a travesty. It's absolutely ridiculous. So that's why we exist, because we know there is great work. If you don't know the work of these scientists outside the mainstream, well, you can visit our websites, beyondmainstream.org. First of all, if you're just getting into this, it's an online magazine for critical thinkers. I think we're coming up to 100,000 views of articles on that. You should check it out. Really super interesting read. We also have naturalphilosophy.org, which is our critical thinking community. Man, it's really hopping, I'll tell you. People are talking, a lot of debate. even people who are supporting relativity against people who are not supporting relativity, and always a lot of interesting chatter there. We have different groups, so you can become a member. It's really great. And of course, if you want to look up uh, work outside the mainstream, you're not going to find it at Wikipedia, because Wikipedia is the consensus, and the mainstream, of course, I'll be talking about that next week, on how the majority is always wrong. So you can go to Wikipedia if you want to know what's wrong. You want to come to wiki.naturalphilosophy.org to see what could be right. Well, because everything's wrong, there's always a better answer out there, but we don't seem to try to pursue that in a formal way in our formal systems, which is sad. We do have memberships, and we do need your memberships. Please, 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 especially if you're a CMPS member. If you think this is a cheap endeavor, it's not. It costs 20 in between $2,200 and $2,300. We've cut it down to the bare minimum for the website, for our StreamYard, which you see today, for our stuff that we use for publishing our proceedings, for all the software that we subscribe to, because today and age you don't buy it, you got to pay a subscription to our server, so it won't be hacked, because they like hacking people who are trying to change the world and give new perspectives. So altogether it does cost us, and of course the server where this runs. So we have our own server where this runs. So it's very important for you to support us monetarily. Anything can help. $35 a year. If you can't even pay that a one-time fee, you can also pay monthly. We have people who are more modestly giving us $5 a month. Got people giving us $25 a month, $50 a month, and annually you can also have an annual gift of 35 all the way up to 500, and donations. And I do want to thank a couple of people, Nick Percival and Dr. Cynthia Whitney and Ramsey, it's his pen name, for their generous donations. Without those donations, we wouldn't make that mark. But please, again, I want to thank all of our annual monthly memberships. It makes a difference. We need your vital support, without a doubt. So please, please, please. And if you have a problem, or if you want to write a check, if you don't like doing things over the internet, contact me, and we have people who send us checks. We have a bank account for, of course, this organization. It's all nonprofit. All the money goes to it. Nobody gets paid. I don't get paid, to the chagrin of my wife, I'm sure. But anyways, coming in 2022, it's hard to believe that I'm saying that. We have invited guests, of course, the best of CMPS conference talks. I'm arranging these things too. We're going to be looking at the dissident science news takes, that is, look at news, see what one of the things is, if you're new to critically thinking and criticizing mainstream in a good way, not just because it's mainstream. I actually get when I do a lot of social interaction, social media interaction, because that's how we get a lot of people in our direction. You go out there, and people who think that social media, especially the older people in our group, think that social media is baloney. Nope, that's where we grow today. That's absolutely where we grow. I get people saying, "Oh, you're for everything that's against mainstream." It's such a petty way to, petty, illogical conclusion. Of course not. The truth of the matter is, it's not we're against mainstream. We looked at mainstream with a critical thought and found all these problems with it. Some of them are ridiculously problematic, and the only way you see that is to study them. It's not that we are like, zoned out, throw away all of science, and then say to ourselves, "Oh, I'm just going to create a new theory of the world." No. In fact, I always say that the people outside of mainstream who are trying to come up with new and fixing the problems and new ideas are the ones who understand mainstream science way more than people in mainstream, because they just teach it and never think critically about it. And we also have, of course, our new historical perspectives in science. And today we have that. We have a lot of other ones coming up as well. Coming next week, I'm going to be giving a talk of why the majority is always wrong. There's a really great I won't tell too much about it, but we're going to talk about that. It is absolutely true, and this is not my thesis. I did not come up with this. Somebody else did, and there's a quite good argument about that. And one of the reasons I do that is to show people, hey, again, thinking outside the mainstream is where things happen. In fact, the majority is always wrong. It's always a minority who ends up being right. So to move science along, Nick Percival is working. He is the expert, I think. Well, at least no, there are other experts, I guess, but he is the expert who's been willing to take on our historical talk on special relativity, the evolving take on the history of special relativity. He's working on that. It's going to be 2 talks, and that's going to be super legal. See, there you go, Portuguese flying out of my mouth. I'm sorry about that. Weird. I speak both every day. I know I'm trying to impress. Believe me, it's not very impressive because both languages suffer. Can't speak English, can't speak Portuguese perfectly anymore. It's just some of this middle thing. But once in a while, you'll hear one of those words pop out. Sorry about that. My dad will be talking about more electron experiments. In fact, he called me to his laboratory in his room and had the simplest setup ever, a wire going over a compass and a battery. And he says, put those together. And then we did it. And then we had some really weird behavior going on. And he goes, I think this is what's happening. So he moved the table to the other side of the room, and sure enough, and it was all predictions from our particle model. And so he's going to be talking about electronic components like the diode, the transistor, and all that in respect to a new model of the universe, a model that makes everything physical. So it's not just empirical equations. So that should be a lot of fun. And then we are going to have debates on special relativity, general relativity, dark matter, and ether. That's one of them. So we're looking to gather some people on doing that. If you're interested in participating in that, it's going to be a lot of fun. It's really interesting is to try to take the side that you don't believe in. And I think that would be pretty wonderful. So my goal is to get at least 2 people on each team. Or if we can get 3, but 2 is probably better for our forum, and to have these debates so people know what those arguments are. You can blame Ian Cohen for this, and I promise he will not participate in any way in this. No, I'm giving him a hard time. Ian's a great guy. And we, of course, have the history of general relativity, light, gravity, magnetism, electricity from a distant point of view. That's coming up. So stay tuned, folks. It's going to be a lot of fun with all these things. But we're going to get here. We've got Eric today. He's going to be talking. I'm going to tell you a little bit about Eric before we bring him on. Again, the title of this series is Evolving Perspectives on the History of Science. And that's the way it always should be. Nothing should be written in stone. This should be done in universities. Universities don't do this, and it's sad. And Eric here is going to talk about something near and dear to his heart is quantum mechanics. Let me tell you a little bit about Eric Reiter. Eric Reiter is a research scientist, inventor, computer scientist, musician, and amateur architect. Yes, sir. His work gained popularity in the early 1970s with new articles in the San Francisco Exploratorium Museum's rag there, featuring his sun harp and solar living pod. This is the early 1970s, folks. That's way ahead of your time for sure. Eric studied physics at the California State University, where he took classes in quantum mechanics. He must have thought a lot about it and disagreed about something. That's why he's here today, I think. In 1980, Eric was a part of the DBA Computer Continuum, where he designed and sold add-ons for personal computers to form signal acquisition control robots. In 1980, folks, I bought my first computer in 1978. My dad worked on, I think it was a UNIVAC computer in 1960. So a lot of people involved in the computer industry. He later returned to college where he studied biology for 2 years. Eric discovered the Unquantum Effect for light in 2001 and for atoms in 2004. He has published his works in several small journals. And of course, why small journals? Well, why does he publish in large journals? Because they don't want to be told things aren't the way they think, even when Eric is right or any of us are right. We all know that. So, and he has applied for 4 patents, one for the photon violation spectroscopy. So that's Eric, a wonderful, obviously, how do you say, out of the box thinker, ahead of his time thinker. That's one of the reasons we've got him on today. So I'm going to bring him up. Hey, Eric, how are you?
I'm good. Thank you very much.
Wow, you sound very impressive in the introduction. I tell you, tell me why do you think you've been always sort of before we start, I always like to interview the person a little bit, get to know them, who they are. Why do you think you sort of just never thought inside the box? Is that was just something normal with you? I mean, you seem to be ahead of the curve of everybody. Tell me why do you think that is with you?
I wanted to see what was going on with the physical world. I didn't believe them when they were telling me what was going on with, especially with the double slit experiment. Right away, as soon as I saw that, I knew there was something wrong with it. And I wanted to go to the experiments to see what the experiments were saying, not people.
Right. It's funny because that's a big problem. When I did my movie Einstein Wrong, it's like, don't listen to me, listen to what I say or what I do. And that's what people don't do. They listen to someone who's in somewhere, the person on TV talks about it or their professor talks about it, writes it on the board. You're looking at it. You seem, you have a logical problem with, especially the double slit problem. I mean, there's just all kinds of problems with that. And yet, did you ever see a professor actually perform that double slit in a setup in school?
No, they don't do that. There's another experiment that scientists concentrate on more when they get more serious, and I'll detail that in my talk.
Okay, okay. So, where do you live right now?
Pacifica, California.
Okay, so you're in the California area. So when do you feel that the times you were growing up with I grew up in the 60s and 70s, where it was a time where people were trying to challenge, I mean, in the 60s especially, right? In the 70s, people were challenging in general. Society was challenging, mainstream everything, politics, philosophy. Was there a climate there at that time, do you think, back then?
Yes, yes. Well, I grew up in San Francisco, and there were plenty of protests going on.
Right.
I'm not sure if you mean in science or politics.
Well, all of it. I'm just saying, I think it was a generation of people who started rejecting what they were told and said, I want to find out myself and see if there are maybe even better ways. It was that there was a climate like that, especially in San Francisco, right?
Yes, yes, quite a bit. Well, more in the politics of it. uh, to see the arguments in the sciences, you have to dig into the libraries for all that. The controversy over quantum mechanics is ever since the 1900s. It's always
Right.
been a controversy.
Right, right, right. Okay. So what we're going to do is I'm going to get ourselves up here. You have your talk here. And for those who want to read more about his you have a website that they can go to, thethresholdmodel.com, where you can get more about this. But what's going to be interesting today, you're not going to see anything that he has on his website today. Well, some of it, of course, you will, but he's going to be talking about the history of quantum mechanics. So thank you very much, Eric, for taking this on. This is a big task. And I'll be here if you need it. And when you go to the board, I will be making sure that the board will be the big picture for now. But I'm going to step aside and welcome Eric, and the floor is yours.
Good, good. All right. The history of quantum mechanics has always been controversial. It's they say shut up and calculate. The the wave particle duality has always caused these arguments. There are many words for it: entanglement, the measurement problem, quantum mechanics, Schrodinger's cat. They all mean the same thing, and people have been arguing over it because it's incomprehensible. I'm going to show you just what that incomprehensibility is, the detail of it. And there were assumptions made along the way, and I've identified specific important assumptions that we can explore and see, well, they were wrong about. So saith Eric that they were wrong. So we'll see that. Uh, there's way too much material to read in my slides. So just look at where I use the cursor. Here, I'm just trying to point out that in red, there were important parts that were not accepted by general mainstream scientists. So 1897, I'll do it in chronological order for the most part. J.J. Thompson figured out how to read the charge to mass ratio of the electron. Now, they were using the particle model, and that was a good thing to start with, at least. Quantization preceded quantum mechanics in the understanding of the atom and charge. And so in this early experiment, he's deflecting charge with an electron gun and capacitor plates. And then at the same time, he puts a magnet on it and straightens out the beam and does equations. And he's able to decipher the charge to mass ratio. Now, my main point here is that the message of the experiment is the ratio, and it's in free space. So very soon afterwards, JJ and his team did an experiment. It's an earlier version of what is more famously known as the Milken oil drop experiment. It was really started in J.J. Thompson's laboratory. And it's about finding the charge constant of the electron. And again, they were using the particle model. But it looks like there is a way of seeing this that is not quite right that I'm pointing out, where they deciphered the charge constant in bulk matter. And then they say that same quantized charge, E, is applicable in free space. But it's a different situation. In free space, it's the charge to mass ratio that we see. So I'm going to point out this idea that in free space, there are ratios that are expressed by our experiments. I'll point out other experiments that have that effect. But this was the first important assumption made about how to look at our constants and experiments, where they use the particle model in both cases, in free space and in bulk matter. And I explain things here. The slides are really for people to read later to get the full effect of what I'm saying, because it's going to most likely be too difficult. All right, 1900, Planck devised his great way of finding the black body spectrum. And there's some confusion in our textbooks where they say it's about quantizing light, but it isn't. Planck made it very clear that there was energy in the radiation, but his resonators were separate and vibrational. And so his equation, where he uses Planck's constant equal to frequency, no, I'm sorry, energy equals Planck's constant times frequency, that's about the resonators in matter. That's my main point here. It's not in light. And this is the first showing up of Planck's constant right here where I show it. So 1902, Lenard, the experimentalist in Germany, figured out how to read the photoelectric effect, where he came up with how the escape energy of charge did not change with the intensity of the light. But he did see that it changed with the frequency of the light. When he went to ultraviolet, he had greater kinetic energy. So he was trying to figure out what was going on, but he made a false assumption, and it is seemingly wrong what he did. He thought it was about tickling like a nuclear decay in a resonant reaction to have charge escape. And that was used as an alternative, that was used as an explanation for the photoelectric effect for a while, even after Einstein, because Einstein's idea was so objectionable. But so I'll point out just what was written here, and so you can see this is from his Nobel Prize lecture, so you could see just what he did and said. So in 1905, Einstein was able to find his the relationship of energy equals what is now called Planck's constant times frequency. He was able to find that simple relationship on his own, but he wrote it in a different way with these three constants that later were understood to cancel out to equal Planck's constant. There's a R, an N, and a beta, and so that's like Planck's constant. And he had the equation right, but he had this model where he said, I'll read it. This is from his 1905 paper. According to this picture, the energy of a light wave emitted from a point source is not spread continuously over ever larger volumes, but consists of a finite number of energy quanta that are spatially localized at points of space, move without dividing, and are absorbed or generated only as a whole. Photons, later called photons. So this flies in the face of all the wave understandings of light, that there's interference where it cancels out constructively and destructively. People did not think this was true, especially Milken, but they thought he was just wrong about this. However, people looked at the equation and they found that it worked. Oh yeah, very soon after, Lorentz, he just said, forget about it. This is just wrong. It's not to be considered, this light quanta thing. And there were other people who said the same thing and experimented and tried to figure out, well, what's going on? 1911, Planck had an accumulation hypothesis, a loading theory, where he shows how energy is loading up with time. It can increase, and then when it reaches a threshold, it can suddenly go down to emit. So the idea is continuous absorption, explosive emission, and this is very close to the model that I've used and developed from. If he actually had on this vertical is energy, but if you do a simple algebra, this loading up part the vertical axis can be action. Action is what Planck's constant is about. So here it's like Planck's constant is a maximum. 1916. Did I skip something? I should also mention that Sommerfeld and Debye had a loading theory where it accumulated and showed up suddenly. So they were given different names. Lenard, which wasn't quite right, he called it a trigger hypothesis. Planck, he didn't really call it anything. I call it the loading theory because Milken called it that. In your textbooks, it'll be the loading theory. No, in your textbooks, they'll call it the accumulation hypothesis. So there are a few different names. Those two, accumulation and loading theory, those are the same thing. All right, we're going to go to Milken. Milken tested the photoelectric effect Other people tested it earlier, but they were not sure about the Planck's constant as being such a simple linear relationship. But he showed it very clearly. This is his data, and the slope of this line is Planck's constant to charge ratio. So the important point here is that the photoelectric effect message, the message of the experiment, is the H to E ratio. So even though in his title he says it's about determining H, the experiment is actually about the H to E ratio. Now, what's even more important is that in this paper, Milken argued against the photon model, and he was considering very strongly the loading theory. So it's good reading about that. Right. So this is from his book, actually. He's predicting the effect that I found, which I call the unquantum effect. And that is that energy can absorb and store up from light, and then it only needs a small addition for it to show up in a pulse later. So that can explain the photoelectric effect and many other experiments, but they didn't understand how it could be. There were many arguments. How could something absorb? Does it get affected by temperature or not? And different ways where they discarded it. In the meanwhile, soon after, Einstein won the Nobel Prize. It was for the photoelectric effect equation, because there were still arguments as to whether the model was right, but they knew the equation was right and how important it was. And so Milken was still arguing against it. So 1923, Compton uses the photon model of light in a scattering experiment where there's incident X-rays. It hits anything with some charge in it. The X-ray will come out with a lower frequency, a longer wavelength, because it loses some of its energy. So they're thinking in terms of energy and particles, and it all works out in the derivation of this experiment. And in this way, here's the recoiling charge. So light comes in, it scatters, and charge gets recoiled. The equation for it is here. And notice in the equation, there's an H to M ratio. And so that is really the message of the experiment, that it delivers this ratio of constants. And this is important in my theory, where I'm saying that action, just the same way Planck did, is a maximum. And that means the M can be less than, the mass can be less than M, the action can be less than H, but the ratio is conserved. So it's a ratio trick that I'm talking about for my theory. So I'm trying to show that in the experiments of what we're taught in quantum mechanics, there's another way of looking at our constants. And so here it is, the H to M ratio. This next part is important, and I'm going to have to read it. It's about energy conservation being understood in terms of particles. If this work on the scattering of X-rays and the accompanying recoil electrons is correct, we must therefore choose between the familiar hypothesis that electromagnetic radiation consists of spreading waves on the one hand, and the principles of conservation of energy and momentum on the other. We cannot retain both. So my point is, the idea of energy conservation is strongly connected with particles. They think that there is no way to see energy conservation unless you use the particle model. And that's one of the reasons why they use it and why quantum mechanics developed the way it was. They think, well, if we don't see anything less than these particles, there's just nothing there. But I have devised a way to see what's there in my experiments. So this is one example of that kind of thinking, and it's all throughout physics, the way they do this, to think of energy conservation in terms of particles, and that's what leads to wave-particle duality and all of this weirdness of quantum mechanics. So 1924, de Broglie devised this equation on the bottom where wavelength is equal to Planck's constant divided by a momentum. And that worked in experiment. However, the derivation I'm pointing out has many problems. I don't know if I should go through all this, but he concocts out of the Lorentz transformation this equation that has phase velocity times a group velocity equals the speed of light squared. And that means if the group velocity, that's associated with the particle. If that's going anything less than the speed of light, then the phase velocity of this wave has to be going faster than the speed of light. And this is regularly used in textbooks and papers to rationalize that the wave nature is just a mathematical ghostly probability wave without any physical significance. So since the equation fits experiment, they go back to this derivation and say, well, maybe there's something with the derivation, and that's evidence the probability wave. And I've devised another way to derive de Broglie's equation, so you don't need this. But this is what's accepted in all of physics. 1924, Bohr, Kramers, and Slater, mostly Bohr, comes up with an idea to say, well, maybe energy is not conserved as particles. And he thinks of it more of a statistical way where the clicks in our detectors can show up more random. And so he predicts that there will not be coincidences in the experiments, especially in the Compton effect. So that inspired the experimenters, Botha and Geiger, to do a coincidence experiment on the Compton effect. And they found there were coincidences. So when Bohr saw this, he gave up on his statistical model and said, well, photons must be right. He was on the right track, according to me, to think that it's not all particles, because particles don't diffract. Particles don't smear all over the place the way waves do. They know full well. So that's been the controversy the whole time, wave-particle duality. So he was trying, but he gave up prematurely because of the false interpretation of this experiment. These experimenters understood that it wasn't just showing photon model, that it could be something in between, but it's in German, and I did look at the German to see what they were saying. So it becomes difficult when papers are not translated and you have to go to the German. But I did that. I went to the original papers with a translator. 1926, J.J. Thompson's son, George Paget Thompson, did an experiment to diffract the charge wave and found that that electrons act like a wave. At the same time, it was done by Davison and Germer. So they discover charge diffraction, a very great set of experiments. But still, they were interpreting it in terms of a probability wave as to what's going on. So Schrodinger devised this wave equation in 1926, which is used to this day, but it was reinterpreted. But let me just show this excerpt here, because it shows what was Schrodinger thinking about going on inside. So he explains that light wave is related to these beats, and the beats are envelopes of waves of his wave function, given this symbol psi. So what Schrodinger was trying to say is that charge is the envelope, or their beats, of psi. And this is the model that I use and I've developed with a few other, with equations relating to important experiments. He had it right, but this is from a later book, but immediately after he introduced his wave interpretation of what was going on with light and charge, it was reinterpreted as a probability by Max Born, and that's the way everybody uses it. The ghost wave I mentioned, the probability wave. Anyway, in this book of lectures by Schrodinger, he says, I'm opposed to all of it. He was against quantum mechanics, how it was reinterpreted, very strongly against it. He understood that the probability thing did not make sense. 1928, a very important experiment where they measure the response time of the photoelectric effect. And so here you can see the data where there's all these times that happen, longer times. It's still in nanoseconds, but it's not just this shortest time of like 1 or 2 nanoseconds. The shortest time is in this experiment is 3 nanoseconds. But I'm going to show you how our textbooks read this experiment wrong. They only say that the experiment gave you 3 nanoseconds. But you can see they gave a lot, all these other times. So there is a longer response time in the photoelectric effect. They did the experiment right, Lawrence and Beams. 1929, Esterman and Stern, actually it was done earlier just by Stern, where they diffract helium. Helium, thought to be atoms, can diffract like a wave. Well, there's a problem with that. Particles don't diffract, but here atoms are diffracting. Well, is it really atoms? I say it's the helium wave function that's diffracting. Anyway, their experiment shows that it fits the de Broglie equation. Lambda is equal to h over mv. So that was pretty great. But they interpret it by the probability equations that we just saw, the probability interpretation of quantum mechanics. Then there were books that described in detail what is a photon. So this is in a later book but it was expressed by Einstein much earlier. And to paraphrase what it's about is a photon goes one way or another at a beam splitter, but it must also go both ways to display interference. Now, this is a contradiction, and this is the beam split coincidence experiment that I do. And I think I should go to the blackboard to try to write to show this in detail just what he's talking about. And so I don't know if you can see, but let me just draw the beam split. And so it comes from the left. He's saying if somehow you can figure out, well, is it a blob of energy? Well, we're not that concerned about just how it's smeared out right now. We're going to just look at what happens at the experiment, because people will do all kinds of things here as to, well, what is the photon? Is it a wave or a wavelet or a blob or what? Here's what's important. It should just go one way or the other. If it goes this way to make a click, it's not going to go the other way at a beam splitter for that instant of time, within a narrow range of time. And there's a simple calculation to say, well, what is the narrow range of time? And everybody agrees on that. So if it goes this way, it won't go that way. If it goes this way, it won't go the other way. Now that is only the first half of the definition of the photon. And it's not just for light. This is for all of quantum mechanics. This is the definition of quantum mechanics. The other half of the definition is that if you were to reconverge the beam, like in a Mach-Zehnder interferometer with the same source, and see what would happen over time, the absorption plane will show up an interference pattern. So it'll get more light, less light, more. That can only happen if it goes both ways. So here you see it has to go both ways to get an interference pattern. But if you were to just look for what happens at clicks over here, it does not go both ways. It goes one way or the other. That is the model of quantum mechanics. And it's not understandable. Nobody understands how this can be, and they test it. We're going to look at tests of this same experiment. So let me go back to my slides. Heisenberg writes the same thing, and he talks about the collapse of the wave function, that it's the ghost wave that can go everywhere. When it shows up in one detector, the wave function collapses over macroscopic space, and this collapse of the wave function is talked about regularly, and it's just too ridiculous, really. There's something else going on, and I know what's going on. It's that it's not a particle to begin with, and these experiments are flawed. And now I could show you that later. I don't think I'll be able to show you the flaws of them now. That'll be in a later talk, or you can see that on my website. 1935, Milken still understands the loading theory, but he doubts it. He thinks it's too difficult to really see as true. He says it's terribly difficult to conceive. So he understands that there's a preloaded state, but he sort of gives up on it. Now, what's interesting is after this date of 1935, I go around looking in all the papers and libraries and books, trying to see, well, does anybody else talk about this loading theory? And do they talk about it in a fair way where there's such a thing as a preloaded state to do it the way Milken understood, where it just takes a little bit more energy and then it can show itself. Nobody does that. Nobody explains the accumulation theory or the loading theory in a workable way after this date. It seems to have been banished in our literature and from people doing experiments on it. 1935. This is really great. In Compton's book, he has a wave derivation of the same equation and the same experiment that he did with particles. So this is a big clue as to what's going on. If you're able to derive an equation using the particle model, you can do it with the wave model. And so he used de Broglie waves, where there was like a grating. I should draw a picture of this. What did he do? So let me go back to the pen board. So let's say it could be done with gamma rays or X-rays. And he's saying that charge is like a bunch of layers where the wavelength in the de Broglie equation is the space between these layers. And this is charge, these layers, and it reflects off of the layers. And so this will be the reflected gamma ray in this case, or the X-ray. But the charge goes this way. And they use the Doppler equation. So a combination of the Bragg equation and the Doppler equation for the movement of charge can derive the same equation as his Compton effect, which is what? Delta lambda is equal to like h over mc, I think it is, 1 minus cosine theta. The equation for this experiment. That's important. So you can do it both ways, and I've seen how to do the derivation of important equations both ways, with the particle model or the wave model. What's about that is that people report the particle model derivation to say that's really what's going on. And nobody talks about this other wave derivation. But it's in his book. It's in Compton and Allison's book. All right. 1935, there was the Einstein, Podolsky, and Rosen challenge quantum mechanics. So even though Einstein had this dualistic idea of photons, he comes around and says, well, let's look at this more carefully. And he actually, I think he had it right here in challenging quantum mechanics in 1935. But everybody else says, no, Einstein was wrong. So he's an interesting character. I say Einstein was wrong in 1905, but right in 1935. And everybody else will say Einstein was right in 1905, but wrong in 1935. Okay, Milken abandons the loading theory. I went the wrong way. Oh yeah. Max Born puts in his book about this element of time in the photoelectric effect. And he gets it all wrong. He's saying, well, let's calculate how long it would take to load up and show itself the way Milken was considering and the way Planck and Compton was considering. But if you were to calculate that time, it would take too long. And he's saying, well, it just never happens. In no case can it be more than this short time that he talks about. So I'm going to elaborate on that later, but he messes things up really badly here in 1935. So there are other experiments that look at the timing. So it's a bit confusing. There are experiments that looked at the timing in the photoelectric effect and also the timing in the Compton effect. So in the Compton effect, there was this review article where they look at the time between coincident pairs, and there were longer time between those two clicks, but subsequent experiments only look for the shortest time because they're only interested in the signature of photons and particles. So it's a strong bias that was developing in the experiments, or what will be published by the experimenters, that would substantiate quantum mechanics. 1964, Bell proposes a test of the challenge that was proposed by Einstein, Podolsky, and Rosen. We'll see that that was actually enacted. Here, this is important. Our textbooks handle the element of time in the photoelectric effect, and they make you calculate how long does it take to load up, and you'll get some seconds. And then they'll say this, and I'm just quoting them right here. However, no time lag has been detected under any circumstances. The early experiments setting an upper limit of a nanosecond on any such possible delay! Exclamation point. This is wrong. They should be lambasted hideously for this. So, and all the textbooks do this. I've looked at many textbooks and accounts of this, and they get it wrong. What's also important to understand is that this calculation can be extended to a much longer time if you understand how there's an effect with antennas that can focus so that the antenna can be much smaller than the wavelength of the radio wave that is being absorbed. And so this size of the atom is all wrong because it's very easy to see that it could scale the same way from radio waves all the way down to atoms, and the size of the atom can be much bigger, and it can hold these energies, and you can still make sense out of the element of time in the photoelectric effect. So these are false assumptions I'm pointing out in the way they convince you. It's more like brainwashing what's been happening in all our textbooks to show you that the alternatives to quantum mechanics are not to be considered. According to them, they're making a mistake. It was very obvious that the way they made this mistake, just comparing to the actual experiment that I showed you. All right, this is the result of the Beamsplit coincidence experiment that I was showing from Bohr, and the results of the experiment is this flat band of noise, which is about the time difference in between two clicks. Now, if you put in a source that is two emitted at once, where it can go both ways in the beam splitter, if you test it with not light, with something else, you get this peak in this histogram. So it can go, if it goes to one side first, it'll go click, and then the other side click. So this is a time difference histogram. The point being that when they do the test to see if it's a photon, it shows up with this band of noise. And that's part of the problem. They're looking at noise and saying that is evidence of photons, that it acts this way. And there are other problems with the experiment. So I'm a little out of time sequence. This is a later experiment. And here's the beam splitter. And so there are these problems that I've listed as to what could be wrong, what is wrong with this experiment. They use polarized beam splitters, which will route the light one way or the other. They're only just looking at noise. They're not able to see through to see any important data. I found that these detectors, all of the detectors that go click, like photomultiplier tubes and avalanche photodiodes, they have a dead time. So it messes up the result. It'll make it look like quantum mechanics. And even more importantly, the detectors have inadequate pulse height resolution, and it's hard to explain that. I may get that in a later slide to show you. So now I'm returning to the Einstein, Podolsky, Rosen, Bell test, and all that. It was reproduced. It was done. A good experiment was done where they were able to see that the relationship of the angles. I think I should go to the blackboard to show what this test is. I hope you can see me. So there's something that happens in the middle. It puts out two of their so-called photons at once, and there'll be like a spin up and a spin down correlation to it. So at the detector sites across the lab. So there's an angle how this can be rotated, and I'm going to just call that theta. And the result of the experiment is that this angle versus the coincidences, the coincidence rate between these two detectors, it will show up as like a sine wave. But Bell's theorem predicts that it should be straight lines. So what I'm really trying to say is that in this case, quantum mechanics equals what the experiment shows, and it also equals classical mechanics. Malice's law of polarizers fits this. So classical mechanics. So all three of these agree in this test. So if you were to look in the literature, people argue over this test and everything, I want you to know that there's all this agreement. The disagreement is just in Bell's theory. So who are you going to believe? Are you going to believe all of this or his theory? I'm saying the theory is wrong. There's something missing, and what's missing is a term of this preloaded state that they deny all the time that gives this relationship. So that's what that's all about with this Bell's theorem stuff. and they keep doing more and more experiments. They had it, the experiment right the first time. They try to do more elaborate things about it, which I think is pretty nutty. Um, so we're going to go on. 1985, Feynman comes out with a book where he explains photons, and he's emphatic that light really is these particles. He denies the wave property of light. How he can do that, I do not know. But what's really important is that he does not understand the photomultiplier tube. He says the detector clicks, the pulses that come out, are uniform loudness. You have a one color light, monochromatic light. He's saying the clicks of these detectors are all the same. Well, they're not. This is the distribution of pulse heights that come out from a photomultiplier tube, and this is the occurrence on the vertical. So the horizontal is pulse height. Pulse height is proportional to electromagnetic frequency, and it's also proportional to what they call the photon energy on the horizontal. And so we sort of agree on that on experiments. But the important part of this is that the distribution of pulse heights in all the detectors that are used for visible light is too wide to make the distinction between quantum mechanics and the loading theory. And I go into that here, and I think it's too complicated to do in the lecture, but I explain it. This can be read and hopefully understood later, and it's all on my website. And actually the important point is that if you do it with gamma rays, this turns into a narrow peak, and you can do the distinction between the two models, and that's what I've done. This is an interesting experiment where it's similar to what Esterman and Stern did in 1930 of diffracting helium, but they do it with a grid of holes in circles, a diffraction lens, and they can see both signatures of the particle and the wave. And it's an important clue as to what's going on with matter wave diffraction. Because, of course, the wave particle duality is in matter and light, and you're not going to resolve it unless you handle both. But this is an important clue. Well, for one, it has to go through multiple paths in order to focus to a point in the middle, a localized section where focus is like a wave. This peak in the absorption screen will not show up with particles. It has to be bending around from multiple paths to do this, and they all agree that. They agree that it must be doing that, but they interpret it by the probability wave that's going through, and to say it shows up as particles. So they're still using the probability interpretation here, but also realize the particle signature, when it goes straight through, it makes this plateau on the side. So this is a signature of real particles. So there is such a thing as particles. It can hold itself together as a particle, or it can lose that ability to hold together and spread like a wave. And that's what I'm saying is going on. In these experiments that do beams, they call it a soliton. The soliton is a wave that can hold itself together, but it doesn't have to stay that way. It can lose that ability. It's like an internally held together wave. It can then spread like a wave. It can lose that whole togetherness and then spread like a wave. And that's what's going on with these matter wave diffraction experiments. I'm saying that it really is helium disassociating itself as a particle, smearing out heliumness as a wave. So there are other experiments. The experiment that I did with diffracting helium makes the distinction between the probability interpretation and the loading theory. And I'll have to leave that to another lecture to show that experiment. I diffracted helium. I split helium like a wave right here in my laboratory. And I did it many times, many ways over several years, trying to see, well, did it really do that? Because it was sensational. Okay, I'm concluding here. So there are these ratios that the experiments deliver to us. And there's another way of understanding that where the charge and the mass are actually, if you see them as thresholds, where the action is a threshold, then you can understand that the ratios are what's quantized in experiments in free space, or when they do these beams and when they show wave-particle duality. It's the ratios that are going expressing themselves. When you see equations that are not in these simple ratios with powers on like squares and cubes on these terms, they're not in free space. They're in bulk matter. And so this is what I have figured out as the resolution of wave-particle duality. So you can see just from the history and the analysis of these assumptions that I've pointed out that there's another way of understanding this modern physics without quantum mechanics. So there's a correction that needs to be done to quantum mechanics that removes wave-particle duality. I'm pretty much finished, and I'm open to questions.
Okay, well, thank you so much. Very, very interesting. I want to just make a couple of comments here. I think it's really one of the things what we're hoping with this series, which you've done, Eric, which is just quite remarkable. One of the things when you challenge something, especially quantum mechanics, because you have quantum computing, which almost has nothing to do at all with quantum mechanics, the quantum, right? This craze. Anytime you go against something like that, people assume that you're a person who doesn't know history, that didn't look at how these things developed. And you just showed that everybody I know who has come up with really, I think, pretty brilliant ideas really went back and looked at it. Because when you are looking at something, you want to have a new model or you want a new explanation. If you just try to explain something without looking at the history, you're going to be in deep trouble, because one of the problems I feel with quantum mechanics is that people who are working on it are doing exactly the opposite of what you just showed, which is the understanding of everything and how it got there. They focus on, just like they focus on what you said, which I think was great. I think this is something I wanted to discuss with you. I wrote some notes down while you're talking, that they have this fixation on the signal, right? They have a fixation on the signal. They do not look at the transitional parts of what's going on. And one of the things that you had mentioned that you said was, hey, that's why they say there's no lag time, right? And one of the things that you're talking about is very similar to what my father is doing, and we'll be talking about the transistor, because he's an electrical engineer. If you have an electronic circuit, here it is, you turn it on, you put a battery on it, you have transistors, you have batteries, you have resistors, you have inductors, you have all these things. You turn it on, and then when it's on, you go and measure it. Well, what in our particle model, we're trying to physically explain what's going on. It's extremely important. In fact, it's more important, the transitional thing that's going on in a circuit, for its description of what's going on physically than simply the state of which it is at. So this whole lag time, this important with transition, is something that is really fascinating. Can you tell us a little bit more about what you see as their fixation on just sort of here's a result and not looking at the in between parts of what's going on?
Oh, I did my best. Maybe I went too fast. Uh, I'd have to go back to some slide. Let's go back to the slide of Lorentz and beams. This one.
Yeah, that one really piqued my interest because what you see normally, isn't it, the case that you see the left-hand side and the right-hand side, and they don't pay too much attention of what's going on in the middle. Is that correct?
The right-hand side did not fit the photon model.
Right,
So they only talk about the left-hand side.
right, right, right.
Well, the experiment was not like that. They lied about the experiment, or whatever you want to call it. They were sloppy. Uh, it's inexcusable, but it goes on all the time. So there were these important cases that I'm pointing out. This is the most egregious case, but it's in all the textbooks. It's at the very beginning where they introduce quantum mechanics to make you think that it has to be photons. So
So,
they
so, so when they publish this, is this curve published or just
yes,
the?
this is straight out of Lawrence and Beam's paper.
And so what you're saying is they address the beginning part of what's happening to satisfy their particle model of the photon, and they just completely skip what's happening at the end.
Right.
Well, it's inconvenient for them to skip it. Okay. That is I got that when you said that. That was pretty shocking because I haven't looked into quantum mechanics as closely as you have. The other thing you said, which I think is very telling, and this graph shows it very brilliantly, very obviously, is you said you can't solve all of this unless you explain all of this, explain both the particle and the wave.
Right. Right. Well, let's go back to the just the wave effects, uh, interference. Um, I didn't do a picture of like the double slit experiment, which is just a statement of the paradox. Uh, Everybody knows that waves diffract and interfere and cancel out. Well, at the same time, many have tried to just to see, well, is it possible to make that happen with particles? And it doesn't work. Uh, if you try to interfere, there'll always be two paths to make an interference pattern. And there's no way. People have tried, and they always get shut down. There's no way to get an interference pattern with particles going through. A particle would only go through one hole or the other. And this will happen just with a single slit, by the way. You don't need two slits. You'll still have an interference pattern. So you see interference all the time. Physicists know this, that there are wave properties. This is the essence of wave-particle duality, that you cannot explain the particle-like effects with waves, and you cannot explain the wave effects with particles. Those models are mutually exclusive. So the way quantum mechanics has dealt with this is to make the wave property mathematical. Like it's not physically waving across like a water wave. That is just this math that you do to predict where the particle would show up. But when you do that, you end up with this one way or the other paradox, which is even more horrible than just waves and particles, which is that if it goes one way at a beam splitter, it excludes, does this OR thing. If it goes this way, it excludes the other way. Well, what kind of magical weirdness is that?
Yeah.
That's what they say happens. And
Of
the
course, yeah.
experiments that have been done, they try to say this is true. In many experiments to this day, they'll say this is, but I'm saying that it can't be.
It does
Nature.
that also manifests itself in this idea that there are particles in two places at once?
Yes, that's the superposition.
Yeah.
And the collapse of the wave function and the measurement problem. All of those words mean the same thing. It means this.
Right.
This problem that Einstein pointed out early on in the definition of the photon.
Right. Okay, we've got a question from Jim Marison. It says, Eric, I don't know if you know the answer to the question, but what do you think of David Bohm's pilot waves? Are you familiar?
Yeah. Well, what would, I don't like it. What would make the wave? They try to make a wave that will guide the particle. So let's say it really is a particle that went through one slit or the other. Let's do the double slit. Well, what would make the wave go through? The problem is, if you really think it's particles and that there's a wave that's guiding it, the wave would have to come from the particle. It would have a center here, and it wouldn't be everywhere. That would be needed for the double slit, for instance. That's the problem. It doesn't work. It's a very artificial act of desperation, and it's not been accepted. It's pretty much the same thing as just saying it's a probability wave and shut up and calculate. It doesn't do anything for me, what David Bohm did. So that's my simplistic shot at it.
Okay, so another thing that people talk about, obviously, especially in the dissident group, is ether. Ether, of course, is great with the waves. It's terrible with the particle side of it. So ether, I would I would imagine your answer, just listening to you today, is ether's got the opposite problem of the particle.
Yes, they think that light needs to have a medium to go through, and it's the ether. And then they do experiments like Michelson-Morley experiment, and they say, oh, there's no ether. And then they say, therefore, it's not a wave, it's just particles going through. So the lack of the ether tends to help their probability wave interpretation. Now, I'm in the middle about the ether. I'm not really handling the ether.
Right.
I'm handling wave particle duality is a different, but there's some relationship, but it's a different question to answer as to the nature of the medium that light and charge goes through.
Yeah, I think here's a question from Franklin Hugh, and I think I know the answer. Again, I've heard you numbers of times, and I think what's really interesting about what you're saying is you're not looking at the solution. You're looking at the problem. You're looking at the evidence of the problem. You're stating that the particle people don't have it, can't explain it all. You're explaining the wave people don't have it all, and that you, and as you said, that I wrote down here, you can't solve all this unless you can explain both the particle and the wave.
Right. I'm handling the wave particle paradox, but I'm not answering if there's an ether or not. I'm saying they're different questions, but it's one step at a time. If you can understand what's going on with this accumulation and not have this problem with wave function collapse, then you can attack other things like the ether problem and get that straight. It's one thing at a time.
Right. No, understood. And I think that's been one of my problems myself, is when I look at people, for instance, who do have models for light, for instance, is they don't look at this experiment, which is really the experiment to worry about, to be able to explain. I mean, this is the cause of the problem of whether people can decide whether it's a photon or an ether or whatever it is. And I think what we've ended up with is the experiment has wave properties, it has particle property, it shows both of those. That's what nature shows us. That's what your lab has shown over and over again. And you can look in the history of it, and you have people on the one side, it's the photon. Oh, on this side, Feynman says, no, it's the photon. Then another person says, no, it's the wave. Yet anytime someone goes to solve it, what we have is the particle by itself in isolation doesn't solve it. The wave or ether, for instance, model doesn't solve it. So you have these two sort of almost like Democrats and Republicans that will never agree, but neither one of them are right. I mean, it seems to be that. And I think one of the things that I really think that you're showing here is that you've got to pay it. We've got a lot of data out there. I mean, we've got a lot of experiments that give us clues. Now, those people who want to actually solve it, then, heck, you got a lot of great experiments to look at to be able to explain. I mean, that's correct, right?
No,
Oh, no.
I don't think you really understood. I am showing that there's a resolution of the wave particle problem. It is surmountable.
Yes.
But I didn't get to that yet in my experiment. My experiment looks at this beam split coincidence where they say it goes one way or the other. Okay. That's everybody else. But I made it go both ways. Okay. I defied the prediction of quantum mechanics to show that it isn't a particle that goes one way or the other. It really is a wave. And then I explained the wave properties with those ratios and thresholds. So I claim that I've overcome the wave particle problem. And then there are still other problems that are different about, well, is there an ether or not?
Okay, I got you. All right. Okay, let's see. We have some people in the green room. Anybody want to come up? I see there's James, Kian, Ian, James here. So we're going to bring in James up to. Hello, James. You're muted. You're muted still, James. You are muted. Waiting for Tim to unmute.
Unmute. Okay. Now can you hear me?
Absolutely.
Okay.
Thanks
Hello,
for coming
everybody.
on, James.
I was very excited by, well, first, Eric's presentation today was magnificent. It was really wonderful. An incredible job. Thank you, sir. In the previous appearance of Eric here on the CMPS Saturday sessions, he presented his own experiments. I have found those extremely interesting. And the ones he presented previously. And he sort of touched on some of the ideas. One comment he made that I'd like to offer humbly, if I may, a correction. He said that after, I think it was 1935, I'm looking here for a note, that's why my head is bobbing around. no one was supporting what might be called the loading theory, although he was sympathetic to the loading theory, and some of his experiments may be taken as supporting it. My correction is that my work in binary mechanics supports the loading theory.
Oh, that's nice.
And is consistent with Eric's work. And the second point I'd like to make is that one thing that I haven't heard, well, you can sort of deduce it from what Eric has been saying both today and in previous session and on his website and so forth, that the question of explaining how a particle moves, or how the moon moves, or the Earth, or a galaxy, how anything moves. Physicists have focused a lot on measuring motion, but the job of the physicist is to explain how things move, the mechanism of motion. And in my work, not to take the spotlight off of Eric's splendid work, the law of motion I propose is exactly consistent with what Eric has been proposing, and I'm so excited about it. Ever since his previous presentation, I've been intending to write a paper quoting his work and showing how it's consistent with an explanation of how things move. In other words, smaller entities, which I call quanta, I'm not sure what Eric might call them, and he can say so when I shut up in about 20 seconds from now. A particle moves or changes position by parts of the quanta in it moving to another location, which then becomes, if you will, a new particle, although we think of it as the same particle as having moved. Whereas the number of quanta in the previous location is reduced and it no longer reaches our threshold for being a particle. This agrees with Eric's work, and here's my conclusion, and I'll be quiet, where he, as I understand it, he's claiming that material, or I would call them quanta, I'm not sure exactly what he would call them, are already existent at the destination clicker photosensors, or particle clickers, the photocells and so forth. And that all that's required is the addition of a few more quanta to make it click. And in other words, Eric is on the threshold of actually showing the law of motion that I have proposed, and I'll be quite quiet now. I'm very excited by his work, and I intend to write a paper on it. Hopefully, I'll send the paper to Eric by email so he can say that it's BS or whatever before I actually publish it. But I'll be citing his work in a very positive manner. Thank you.
All right. There is such a thing as quanta, Planck's constant times frequency, and atoms. There is such a thing as particles. But subquanta, I don't think should be thought of as particles or quanta. It's continuous. So we need to make a distinction. What is a particle and what is a wave? The definition I like to use for that is that a particle will hold itself together and a wave will spread all over the place. They're mutually exclusive models, definitions. And I'm asking to hold to that. Now, other people will use the definition of a wave with wave equations, and all that is true and nice, but it misses the point as to what a particle is and how something would go across space. So if you're talking about loading up that is made out of smaller particles, there's no evidence for these smaller particles unless you're very tricky in the experiment to set it up to see this 2-for-1 effect that I've discovered. So it still shows itself as if a particle hit there. But if you start with one at a time and you get two at a time, what does that mean? It means there was something there ahead of time and it was not quantized. So,
well, I'm not sure if I could jump in here, Eric, how you're using the term quantized, but I'm very happy with your statement that something was already there, and it was added to by something arriving, and that is the mechanism of motion. We think that, let's say, an electron is at point X and then it moves to point Y. Quanta within the electron, which I've defined, by the way, move. Some of them move, and so that what was an electron at point X is no longer an electron. It's just a few quanta sub-threshold, if you will, for definition and detection as an electron in our laboratories. And at point Y, the enough quanta appear so that it meets the criteria for us to say, hey, there's an electron at Y. But excuse me, but actually a whole electron didn't move from point X to Y.
It's too confusing to call it quanta if you're talking about underneath the threshold. As soon as you use the word quanta, it's particleized and it holds itself together. So it's not necessary, and there are no signatures in our detectors that show a subquanta. When it goes click in all the detectors and experiments, it's always this quanta like or Planck's constant times frequency. But yet it shows wave properties. So it's too confusing to me to hear you say that there's other little quantas going on that load up. It's continuous. It does not have to be quantized when it smears as a wave. See, that's the wave particle problem that people get all hung up on. They wonder, well, it shows up as a click on our detector screen. It must have been a whole quanta that showed up. Yet it makes an interference pattern. Well, to get around that problem is to give up quantization when it acts like a wave. When it acts like a wave and smears out all over the place, it really is a wave. But there are mechanisms that show loading up to explain the particle-like effects. And that's explained by looking at our constants as being thresholds instead of quantization. So the idea of a threshold is, let's say I have a cup. I want to, I'll say there could be any amount in the cup, but if I was to spill it all over, I'm saying it only spills over when it fills the top. This is the threshold concept. You don't see the water unless it reaches the top, and then it all spills out. I happen to have water in here, so I can't spill it. So you won't know how much is in there. But when it reaches the top, it all spills over and shows itself. That's the threshold concept. That's what I'm saying is going on. But it's hard to see it unless you know that ahead of time. So what goes on is that you can have one cup full, you throw it at another pair of cups, and the two pair of cups can be halfway full. Let me draw this. Let me draw the threshold concept so you know what I'm talking about. You have one whole cup. You spill it over, you throw it. There'll be two other cups here. They happen to be halfway full. Okay? But you don't know it That's the trick. That's what nature is playing on us. We only see when it reaches the top, it all spills over. So if you throw a hole at two halves, then it'll make both of them go to the top, and then they'll both spill over. That's the 2-for-1 experiment that I did. It's very tricky to say that there had to be something there ahead of time that was not quantized.
Yeah, no, I mean, I understand that, and when I see the quantity, what I find is the quanta is that people throw around these words a lot, but they don't think of really anything that represents them, right? What you're saying is that one person asked the question. Let me go back to it. The question was, oh, thank you, James. I'll take you down. Thank you, James.
Thank you.
Yeah. One question is, what's smearing, right? This is the question. You've mentioned smearing a couple of times.
What's smearing?
Yes. It's not cream cheese, right? It's the wave.
In the case of light or charge or matter, let's just take them one at a time. In the case of light, it's just an electromagnetic wave that's not quantized. I'm saying with light, it's not quantized at all. It's emitted in a burst and detected in a threshold that gives the illusion that it would go across space as quantized. So for light, it's always just a smear going everywhere, just waves. For charge, it's a little bit different. In free space, when you do these beam experiments, charge will smear out. But in bulk matter, when you have higher frequency nuclear waveforms to hold it together, it can still have a size, more or less. It'll fall off as a function. It'll be more particle-like in bulk matter. And that's why in the oil drop experiment, they're able to extract the charge constant. It does tend to threshold itself and show itself as a particle. So it depends on whether you're talking about light or matter. And so for atoms, it's harder to picture what would be going on because the experiments of diffracting helium are really saying that it's not particles. Now, if you want to go back to the probability interpretation, you're back with that problem of collapse of the wave function and endless arguments over wave-particle duality, where you think that it's just a probability wave, and they'll say, shut up and calculate, that it really works that way. But no. To escape all these problems is to understand that it's the helium nuclear wave function that really is spreading out and can transmit a signature of its heliumness in the wave, unquantized, and it can load up in bulk matter until it shows itself as helium, as particles in bulk matter. So that's my resolution. And you see that in the combination of my experiment plus this last experiment that I showed, this one, where it has both properties. So if you were to try to say it's a probability wave and it's really particles, you're ending up back with that problem of one way or the other and collapse of the wave function. That's what everybody else says. That is the measurement problem. That is entanglement. That's what everyone has been arguing over for 100 years. And the reason they do that is because no one has come up with an experiment to show otherwise. Well, that's my experiment. My experiment shows otherwise, that if you do the beam split with helium, and so you can see in my work that I took a gold foil and had a radioisotope of americium-241, and whatever's going across space, it can go through one way, and this is gold. It's AU. Now, some of it will reflect, and some will go through. So I have a detector here. I'm describing my beam split experiment with helium, which is really important. Here's another detector. And the detectors go click. And the size of the click tells you the kinetic energy to see that they really are full pulses. They're not deuterons or half heliums or anything. And they know that from other experiments. So we see full clicks from each detector. Well, what does that mean? It means that it's not a particle that one way or the other. The matter wave splits as a real way to both ways to load up. That's my message, that it really can split, violating the predictions of quantum mechanics. It changes everything. So I did, this is the matter wave split experiment. And then the other one, and I did it many ways, many times, to show that this works with gamma rays.
Yeah, that's one of the things that my father and I also see when we look at these experiments, is that when they assume one thing is going on, it's not. When they assume they're shooting one thing, it's not necessarily what they think, that it's actually going in two places. This idea that when they have, like you said, what's the absurdity of a particle, this, whatever they're shooting at it, right? Whatever they're shooting at it, to go in that one direction, right? The absurdity is when you draw the beam splitter, right? And you have the two, I mean, and you say, oh, it goes this direction. What you're saying, it goes in both directions.
The absurdity is to assume ahead of time that it's a particle to begin with.
Right.
We don't know that. We only know what happens at the end.
Right. And my father came and I came up with the same problem, is that you this just doesn't make sense. You can't, the idea that if you think, for instance, this is a simple thing. My dad and I have looked at the beam split experiments extensively. The idea that says, I am now shooting one photon, right? Well, if you look at the experiments, there is nothing they are doing that says that this is really one particle. You know how they tell whether it's one particle or not? They have a detector, which they say has the energy of a photon. And then when it hits that, they say it's got to be one photon because it's made the click.
Now, actually, it's much more complicated than that. So they understand this problem as to what is there to start with. They address that. And in this drawing of the more modern experiment where they're trying to sort it out, they have a source in the middle, and there's a detector on both sides. So they use a source that emits two at once, and they're able to do a triple coincidence to try to say we have one photon at a time.
Right.
So there are strategies to address what is it to start with that they're working with. And there are but there are holes in this argument that I point out in this list here, and it's still very noisy, and I'm not convinced. If this was really true, then nature would be pretty crazy. So the way I get around it is a better test that uses not visible light. to go to gamma rays where it gets around this problem of the pulse height resolution. This is something that I've identified,
Right.
that their detectors don't have this resolution. So if I have to read my own because I get confused. In the experiments that deal with all of those one way or the other photon tests, they never talk about where they set the threshold as to what height of pulse are they using. They don't talk about that. I look at all their papers. They never talk about it, but they should. But they do use pulse height detectors, discriminators. They use discriminators or filters that say the pulse height has to be this high, then we're going to read it. If otherwise, they would be looking at all this noise. So if this gate was set too low, the small pulses can cause pulse pairs that favor the loading theory if you set the gate too low. If the gate is set too high, like up here, it eliminates pulses that would favor the loading theory. So what I'm getting at, this width of pulse heights is not able to make the distinction between the loading theory and quantum mechanics. But they don't address this. They don't say where they set the thresholds. They never talk about it. And so I get around that by using a source that has a narrow peak here that gets around this problem. So, and then there's the test that's used in gamma rays to say, how do you know it's one at a time? So there's a much better test that's used to tell that it's a source that's one at a time for gamma rays. And so you'll have some source in the middle, and you have a detector on one side and a detector on the other side. And if it was to put out two gamma rays, they'll go in arbitrary directions. And so it might go zing that way and then this way. And you'll catch it. You'll catch it in a coincidence circuit that reads when it goes to both. Then you know it does emit two at a time. So some radioisotopes will do that, and they do a lot of tests using this technique, the coincidence technique with this geometry, to see, well, does the radioisotope only emit one at a time? If it emits one at a time, then that graph of time difference with zero will show up as just a bunch of noise. If it goes two at a time, it makes a great big peak here, and you'll know it right away. So I use a gamma ray source that emits one at a time. When it's in this geometry, you get a band of noise just here, and you see that it equals chance. It only goes one way or the other, except by chance. If it goes to both ways, it's just a low accidental chance rate. So this is how you know it emits one at a time. Then what I do is I take all the settings and the source, everything the same, but I move this detector to the back, okay, and have it go through both detectors and see if it goes to one or the other. And so this is equivalent to the beam split. Instead of it looking like a beam splitter, it's one in front of the other, but the energy is the same the way it splits. It splits off some of the energy in one detector, and by quantum mechanics, it should not go to the other detector.
I have a question. You keep saying 1 and 2. 1 and 2 what? It emits one
gamma ray.
Okay, a gamma ray. So what's that?
What's a gamma ray?
No, I know what it is technically. I mean, you have the electromagnetic spectrum, but I'm saying, what is a one of that?
It means it makes a click on the detector. It means just what I'm showing on these experiments. I'll go back to the other experiment.
So yeah, okay. So that the answer is it makes a click on the detector. It doesn't really tell you what it is. It just makes a click on the detector.
That's how we know what things are, is by
Right.
what.
Understood. Yeah. Well, I understand. Okay. I've got a couple other questions here. I want to just get to them before we wrap this up. So, I mean, this has been great. Wish we had more time, actually. We'll have to, I'm sure I'm going to have to bring you back because it's way too fun and interesting to talk with you, Eric, all the time. Let's take a few things. Justin Fousen says, he says, I think we're missing a key component in the experiment, and that's time. We see that photo multiplier pulse height graph with these events, but how much further information could we garner? And I think he's got some more coming here. Could we garner if there was a pattern to the events over time, or if there were none?
Well, if you're talking about this photo multiplier graph that I have on the screen, that's over time. And you want to see that accumulate over like a minute. But my experiments are about nanosecond timings of what goes on. I'm handling time. That's what the coincidence test is about.
Right.
And really what it's about is comparing to accidental chance rates. So you use a simple equation for chance, which is the chance rate is equal to the rate of clicks in one detector times the rate of clicks in the other detector times the time that you use to say within how many nanoseconds you're counting. So this tau, let's say you set it at 100 nanoseconds, some number. Well, when you read the coincidences, you're going to count how many happen within this time frame. Then you look at this equation and you look at the rates in one and rates in the other, and you use that same time that you used in the previous experiment, and you see, well, did it multiply out to equal accidental chance, or was it better than chance? So the clicks should, by quantum mechanics, if it's one at a time, this should just be chance. It should just go one way or the other. And so you'll get chance here. This chance rate will equal the experimental rate. So it's about comparing the rate of the experiment going into a coincidence thing to the chance rate. That's what my experiments are about, comparing to chance. And they're all, so there's a video that I did to show just how it goes over time. I have it well documented and how I adjust everything.
Okay.
It's all on my website.
Okay.
I hope I've answered.
No, it's been absolutely great. The discussions have been flying in the comment area, and we are coming up to the end of our time. But that was absolutely fascinating. I'm very happy, Eric, because you're the first person to talk with our new idea of the evolving observations of the history of science. And you just hit it out of the ballpark in the sense of giving us a really great and detailed history of quantum mechanics, the problems they have with it, and not only that, a viewpoint that's very different, that's looked at it, that shows that we critical thinkers just don't come out of the blue with an idea. That you look at things that you do is you look at the history very carefully. You critically look at it. You don't have to worry about taking sides or you losing your job because you say Einstein's wrong here and he's right here. you're not going to have those problems. And I think that's what we need in science in general. So, and then after looking at it, you make experiments. I mean, my dad's sitting in his lab making experiments, and other people like yourselves are sitting in labs doing experiments. And that is absolutely fantastic. So I want to thank you very much for this. Unfortunately, or fortunately for you, I'm going to ask you back again to talk again about this.
I'd like that.
Yeah, and I think there's just left a lot of questions, and I think we can revisit this. And it takes time for people to get the gist of it, but certainly I want to thank you for your lifetime of work that you have done over the years. It's absolutely phenomenal, and people like you should be looked at way more. And I think that's what the idea of this is to do. So thank you very much.
Thank you, Dave.
All right. All right. Well, thank you very much. That was absolutely fantastic. I do want to thank everybody. I'm sorry I didn't get to everybody who I know there's another person that came into the green room, but I promise you we're going to have him back. And want to thank Eric very much. And we got to get out of here because we are past our time. Well, we're right on the nose. So let's take it out. And as I always say, stay critical, stay thinking. I am David D. Hilster, your science therapist who can't talk very well, trying to get you to the promised land of becoming a critical thinker. That's what we need. We should be able to criticize anything, think of anything that is gone wrong in mainstream, and feel free to do that. And we have that. That's they can't stop us. Can't stop our brains thinking of looking at what mainstream science gives us and being critical of it to make it move forward. That's the way it always works. And next week, we're going to be talking about it. The theme of next week, I'm going to be giving a talk, is the majority are always wrong. See you there.